There's something humbling about standing beneath a sky full of stars, isn't there? That quiet moment when you look up and feel the weight of countless unanswered questions pressing down on you. For thousands of years, humanity has gazed at the cosmos, whispering those questions into the dark. What's out there? Are we alone? How did all of this begin? But here's the thrilling part. We're living in an era where those whispers are finally being answered. Thanks to a revolution in technology, the universe isn't just a distant mystery anymore. It's a puzzle we're actively solving, piece by dazzling piece. Think about this. Right now, telescopes powered by artificial intelligence are scanning the depths of space, spotting planets and phenomena we never knew existed. Quantum sensors, so precise they can detect the faintest ripples in spacetime, are opening windows into the birth of the cosmos itself. Even the boundaries of our solar system are being redrawn by probes equipped with instruments straight out of science fiction. These aren't just incremental steps, they're leaps that are rewriting textbooks in real time. And the most exciting part, every discovery feels like peeling back a layer of the universe's deepest secrets, revealing truths that were once locked away in the dark. So why does this matter to you? Because these aren't just scientific breakthroughs, they're human breakthroughs. Every time we uncover a new piece of the cosmic puzzle, we're answering questions that have haunted us since the first campfire stories were told under the stars. This isn't just about distant galaxies or abstract physics. It's about connection. It's about understanding our place in something infinitely larger than ourselves. And that's exactly what we're diving into today, how the latest technologies are pulling back the curtain on the universe's greatest mysteries, bringing us closer than ever to truths that once seemed forever out of reach. So let's begin this journey together, because the cosmos has been keeping secrets long enough, and the time to uncover them is now. The night sky has always been humanity's oldest storybook, filled with tales written in starlight, but for the first time in history, we're not just reading those stories. We're rewriting them. Take the James Webb Space Telescope, for example. This isn't just another instrument pointed at the heavens, it's a time machine. With its infrared eyes, it peers through cosmic dust, capturing light that's been traveling for over 13 billion years, showing us galaxies as they were just moments after the Big Bang. And here's what's truly staggering. The data it sends back isn't just a snapshot. It's a Rosetta Stone, helping scientists decode the chemical makeup of distant worlds, uncover the birthplaces of stars, and even spot water vapor swirling around planets light years away. But the revolution doesn't stop there. Imagine a telescope so powerful it doesn't just observe the universe, it listens to it. That's the promise of gravitational wave detectors like LIGO and Virgo. These aren't your grandfather's observatories. They sense the faintest tremors in spacetime itself, ripples caused by collisions between black holes so massive they warp the fabric of reality. Just a decade ago, these events were theoretical. Now we're cataloging them like weather reports, piecing together a map of the universe's most violent and energetic phenomena. And then there's the silent hero of this cosmic revolution, artificial intelligence. The universe generates more data in a single night than all the books in the Library of Congress, and sifting through it manually would take lifetimes. But machine learning algorithms can spot patterns invisible to the human eye, like a faint dip in a star's light that betrays an orbiting planet, or a subtle wobble in a galaxy's spin, hinting at dark matter's invisible grip. These tools aren't just assistants, they're co-discoverers, turning raw data into eureka, moments at a pace that would have left astronomers of the past breathless. What's truly thrilling is how these technologies aren't working in isolation. The James Webb Telescope's discoveries feed into supercomputer simulations, which in turn guide the next generation of space probes. It's a virtuous cycle of curiosity and innovation where every answer sparks 10 new questions. We're not just observing the cosmos anymore, we're in conversation with it. And with each breakthrough, we're realizing that the universe isn't just stranger than we imagined. It's stranger than we can imagine, and thanks to these tools, we're finally starting to catch up. Artificial intelligence is doing something remarkable in astronomy. It's giving us new eyes to see the universe. Picture this: every night, telescopes around the world collect mountains of data, more than any team of scientists could analyze in a lifetime. But where humans might overlook a faint signal or dismiss a blip as noise, AI thrives. It scans these cosmic haystacks with inhuman patience, finding needles we didn't even know existed. Take the Kepler 90 system, for example. When NASA Kepler telescope gathered years of light measurements from distant stars, it was an AI developed by Google that spotted the subtle, rhythmic dimming of a star, evidence of an eighth planet hidden in the data. A world that had slipped past human researchers for years was uncovered in days, proving that AI isn't just a tool, it's a partner in discovery, and that's just the beginning. AI's ability to recognize patterns is unlocking some of the universe's most elusive secrets. Fast radio bursts, those mysterious millisecond flashes of energy from deep space, used to be rare and unpredictable. Now, machine learning algorithms comb through radio telescope data, flagging these cosmic signals faster than ever before. Some of these bursts repeat in ways that defy explanation, hinting at phenomena we've yet to understand. Then there's gravitational wave astronomy. When two black holes collide billions of light years away, they send ripples through space-time so faint that detecting them is like hearing a whisper in a hurricane. Yet AI-powered systems at observatories like LIGO can isolate these whispers from the noise, turning what was once invisible into something we can study in detail. What makes this even more exciting is how these systems learn. Every new discovery trains the AI to be sharper, more intuitive. It's not just about finding what we're looking for, it's about stumbling upon things we never thought to search for. Dark matter, the invisible glue holding galaxies together, has eluded direct detection for decades. But AI is now mapping its influence by analyzing the subtle distortions in light from distant galaxies, piecing together a shadowy cosmic web we can't see but know must be there. And when it comes to the search for life, AI is scanning the atmospheres of exoplanets, hunting for chemical signatures, oxygen, methane, even industrial pollutants that might hint at something extraordinary. A world not just like ours, but one that's alive. The beauty of all this, we're not just outsourcing the work to machines. These breakthroughs are deepening our own understanding, pushing scientists to ask better questions. When an AI identifies an anomaly, it's often the start of a new mystery, a clue that sends researchers racing to telescopes and whiteboards. The universe has always been full of surprises: supernovas that explode differently than predicted, galaxies that spin faster than physics allows. Now, with AI as our guide, we're finally catching up to those surprises faster than they can slip away. The cosmos has been waiting for us to listen. Thanks to artificial intelligence, we're not just hearing it, we're starting to understand what it's saying. While artificial intelligence helps us decode the cosmos from afar, another revolution is happening at the smallest scales, where the bizarre laws of quantum physics collide with the universe's biggest mysteries. Dark matter, that invisible cosmic ghost that makes up 85% of all matter, has slipped through our grasp for nearly a century. Traditional detectors sit in deep underground labs, waiting for a rare collision with a dark matter particle that might never come. But quantum sensors are flipping the script. Instead of waiting in the dark, these devices listen to the universe at a level of precision once thought impossible. Imagine a detector so sensitive it can feel the gravitational pull of a single snowflake landing on Mount Everest. That's the power of quantum entanglement, where particles become linked across space, reacting instantly to the faintest disturbances. Projects like the quantum experiments at space scale, or QUES, use this phenomenon to hunt for dark matter's subtle fingerprints, whether it's a whisper of energy left behind as particles pass through Earth or a distortion in spacetime itself. And here's the game changer. Unlike traditional methods that rely on brute force collisions, quantum sensors don't need dark matter to smash into anything. They can sense its presence through the faintest ripples it leaves in the quantum field, like tracking a ghost by the chill in the air. The implications are staggering. If these experiments succeed, we won't just confirm dark matter exists, we'll finally understand its nature. Is it a sea of undiscovered particles, a cosmic relic from the Big Bang? Or something even stranger, bending the rules of physics as we know them? Quantum sensors are our best shot at answers, probing realms where conventional physics breaks down. Already, labs worldwide are reporting anomalies, tiny, unexplained signals that could be the first hints of dark matter's shadowy presence. What's truly exciting is how this ties into the bigger picture. Dark matter isn't just a puzzle, it's the scaffolding of the universe, the hidden force shaping galaxies and guiding their motion. Without it, stars would fly apart and cosmic structures would never have formed. Solving this mystery wouldn't just fill a gap in our textbooks, it would rewrite our understanding of reality itself. And with quantum technology leading the charge, we're closer than ever to pulling back the curtain on the universe's best-kept secret. If the James Webb Space Telescope feels like a leap into the future, wait until you hear what's coming next. The next generation of space telescopes isn't just improving on what we have, it's shattering every limit we thought was unbreakable. Take the Nancy Grace Roman Space Telescope, set to launch in the next few years. While Webb specializes in infrared, Roman will act like a cosmic wide-angle lens, capturing vast swaths of the sky with Hubble-like clarity, but a field of view 100 times larger. Imagine mapping millions of galaxies in a single sweep, or spotting rogue planets drifting between stars, worlds so dark and distant they've been invisible until now. But here's the real kicker. Roman will tackle one of the universe's most perplexing mysteries, dark energy. By measuring how galaxies bend light across billions of light years, it could reveal whether this mysterious force is constant or growing stronger, pulling the universe apart faster than we ever feared. Then there's the European Extremely Large Telescope, or ELT, rising from the mountains of Chile. This isn't a space telescope at all. It's a ground-based behemoth with a mirror nearly half the length of a football field. Using adaptive optics to cancel out Earth's atmospheric blur, it'll achieve resolution 16 times sharper than Hubble. What does that mean for us? For the first time, we might directly image Earth like exoplanets, not just detect them as specks of light, but see continents, clouds, even signs of vegetation. And when it turns its gaze to the earliest galaxies, the ELT could spot something even more startling: population 3 stars. These hypothetical giants, made purely of hydrogen and helium from the Big Bang, have never been observed. Finding them would be like uncovering fossils from the universe's first moments. But the revolution doesn't stop there. Projects like the Habitable Worlds Observatory aim to block out starlight so precisely that faint planets orbiting nearby stars become visible. Think of it as cosmic photography with the ultimate lens cap, allowing us to analyze atmospheres for oxygen, methane, or even industrial chemicals that might hint at civilizations beyond Earth. And let's not forget the Square Kilometer Array, a radio telescope network so sensitive it could detect airport radar on planets light years away. Together, these instruments form an unstoppable alliance, each filling gaps the others can't touch. What's thrilling is how these telescopes complement each other. Roman's wide surveys will flag targets for Webb's detailed scrutiny, while the ELT's razor-sharp images ground truth their findings. It's a golden age of cosmic teamwork, where every observation builds toward answers we've chased for millennia. Are we alone? How did the first stars ignite? What fate awaits the universe? The tools to solve these puzzles are no longer dreams, they're being bolted together in clean rooms and atop remote peaks, ready to rewrite the story of everything we know. We've built telescopes to see across the universe and detectors to listen to the quantum whispers of dark matter. But what if we could reach out and touch the stars? That's the audacious dream behind Breakthrough Starshot, a mission so bold it sounds like science fiction. Picture spacecraft no bigger than a postage stamp, propelled not by rockets but by the gentle push of light itself. These nanocraft, called star chips, would ride beams of powerful lasers, accelerating to 1/5 the speed of light, fast enough to reach Proxima Centauri, our nearest stellar neighbor, in just 20 years. For context, that's a journey that would take today's fastest probes tens of thousands of years. The engineering challenges are staggering, but the solutions are as ingenious as they are futuristic. Each star chip would carry microscopic cameras, sensors, and even tiny thrusters, all packed onto a gram-scale wafer. Their sails, thinner than a human hair, would catch laser pulses fired from Earth, riding them like cosmic surfboards into the void. And here's the real magic. These probes wouldn't just fly blindly. Autonomous navigation systems would steer them, correcting their course with precision no human operator could match. Imagine threading a needle from 4 light-years away. That's the level of accuracy required to snap close-ups of Proxima b, the potentially habitable planet orbiting that distant star. But why Proxima Centauri? Because it's more than just the closest star. It's a testbed for humanity's interstellar future. Proxima b sits in the Goldilocks zone, where temperatures might allow liquid water. Starshot's fleet could analyze its atmosphere for signs of oxygen or methane, hunt for surface oceans, even listen for electromagnetic whispers of alien technology. The data they beam back via tiny lasers aimed at Earth could answer the ultimate question. Are we alone? Of course, the hurdles are immense. A laser array powerful enough to push these probes would need to be 100 million times stronger than any ever built. Dust particles in space, no bigger than a grain of sand, could vaporize a star chip on impact, and communicating across 4 light-years would require receivers more sensitive than anything we've engineered. Yet every one of these challenges is being tackled right now, in labs from California to Sydney. Breakthroughs in photonics are shrinking laser systems, while new materials like graphene promise sails that can withstand interstellar debris. What's most thrilling isn't just the science, it's the philosophy. Starshot isn't just a mission, it's a message. By launching probes that will outlive us by millennia, we're planting a flag not just for our generation, but for all of humanity. These tiny craft, barely visible to the naked eye, carry the weight of a species daring to reach beyond its cradle. And if they succeed, the data they return won't just rewrite textbooks, it'll redefine what's possible. The stars have always been the backdrop to our dreams. With Starshot, we're taking the first tangible step to walk among them. Gravitational wave astronomy has given us ears to hear the universe's most violent symphonies, collisions so cataclysmic they warp the fabric of spacetime itself. When LIGO made its first detection in 2015, it wasn't just a technical triumph. It was like discovering a new sense. Suddenly, we could perceive black holes merging billions of light years away, their final death spirals sending ripples through the cosmos that LIGO laser beams caught like a spiderweb trembling in the wind. These aren't just cosmic curiosities. Each collision is a Rosetta Stone, revealing how black holes form, grow, and reshape their surroundings in ways light-based telescopes could never show. But here's where it gets even more extraordinary. LIGO and its ground-based cousins are just the beginning. The Laser Interferometer Space Antenna, or LISA, will take this revolution to space, where it can listen for lower frequency waves, the kind emitted by supermassive black holes dancing at the hearts of galaxies. Imagine catching the moment when two of these giants, each weighing billions of suns, finally collide. The energy released would eclipse every star in the observable universe combined, yet leave no flash of light, only a vibration in spacetime itself. LISA sensitivity could also uncover something even more profound: primordial gravitational waves, echoes from the Big Bang's first trillionth of a second. These faint whispers would be our closest window to the birth of everything, a snapshot of the universe before atoms or even photons existed. What makes gravitational waves so transformative is how they complement traditional astronomy. Light can be absorbed, scattered, or obscured by cosmic dust, but spacetime ripples pass through everything, carrying undistorted signals from events hidden behind galaxies or buried in the cosmic dark ages. When neutron stars collided in 2017, gravitational waves alerted telescopes worldwide, triggering a frantic race to capture the aftermath of a kilonova explosion that forged gold, platinum, and other heavy elements in its wake. Without LIGO hearing, we might have missed it entirely. The future of this field is brimming with possibility. Next-generation detectors like the Einstein telescope will dig even deeper, hunting for intermediate mass black holes or exotic objects like cosmic strings, theoretical defects in spacetime left over from the universe's infancy. Some theories even suggest we might detect waves from higher dimensions if they exist. Every new observatory adds another layer to our cosmic hearing, turning what was once silence into a chorus of discovery. Gravitational waves aren't just another tool. They're rewriting the rules of astronomy, proving that sometimes to see the universe clearly, you first have to listen. Think of the universe as an endless, ever-expanding tapestry, threads of galaxies stretching across billions of light years, woven together by gravity, dark matter, and something even more elusive, dark energy. For decades, this mysterious force has been pulling the cosmos apart at an accelerating rate, defying everything we thought we knew about gravity. But now, thanks to instruments like the Dark Energy Spectroscopic Instrument, or DESI, we're not just observing this cosmic tug of war, we're mapping it in 3 dimensions, layer by layer, like peeling back the pages of a history book written in starlight. DESI isn't your average telescope. Perched atop a mountain in Arizona, this powerhouse doesn't just take pretty pictures. It captures the fingerprints of millions of galaxies, decoding their light to reveal their composition, distance, and motion. Each galaxy's spectrum is like a barcode, telling us how fast it's moving away from us due to the universe's expansion. But here's the genius part. By measuring thousands of these galaxies at once, DESI stitches together a 3D map of the cosmos so detailed, it shows the subtle wrinkles in spacetime where dark energy's pull is strongest. This isn't just a snapshot, it's a time lapse of the universe's evolution, showing how clusters of galaxies formed, collided, and drifted apart over billions of years. The scale of this project is staggering. Over 5 years, DESI will catalog more than 35 million galaxies and quasars, some so distant their light dates back to when the universe was a quarter of its current age. But the real treasure lies in the patterns hidden within that data. See, galaxies aren't scattered randomly. They cling to vast, invisible filaments of dark matter, forming a cosmic web. By tracing this web, Daisy can measure how dark energy has fought against gravity's pull, stretching the universe's structure thinner over time. Already, early data hints at surprises like whether dark energy's strength has changed over cosmic history, or if our very understanding of gravity needs rewriting. What makes this so revolutionary isn't just the sheer volume of data. It's the questions it could answer. If dark energy's push is growing stronger, the universe might face a big rip where galaxies, stars, even atoms are torn apart. If it's weakening, gravity could one day reverse the expansion, collapsing everything back into a fiery crunch. Or perhaps dark energy isn't a force at all, but a sign that Einstein's theory of relativity breaks down on cosmic scales. Daisy maps are more than charts, they're a mirror held up to the universe's fate, and with every new galaxy plotted, we're one step closer to reading our own destiny in the stars. This is the beauty of modern cosmology. We're no longer passive observers squinting at the dark. We're cartographers of the invisible, turning the universe's secrets into something we can see, touch, and finally begin to understand. The cosmos has spent 13 billion years hiding its truths. Thanks to projects like Daisy, the era of cosmic whispers is over. Now the universe is speaking loud and clear, and we're learning its language. There's a reason scientists call neutrinos the universe's ultimate ghosts. These nearly weightless particles pass through planets, stars, even you, at nearly the speed of light, leaving no trace behind. Billions stream through your fingertips every second, yet you'd never know it. But what makes them so extraordinary isn't just their stealth, it's their stories. Born in the hearts of exploding stars, colliding black holes, and other cosmic cataclysms, neutrinos carry secrets from places light can't escape, and now, for the first time, we're catching them. Buried deep beneath the ice of Antarctica, the Ice Cube Neutrino Observatory is hunting these phantoms. Picture a detector so vast it spans a cubic kilometer of pristine ice, lined with thousands of light-sensitive bulbs waiting for the rarest of events, a neutrino colliding with an atom. When that happens just once in a blue moon, it creates a flash of blue light known as Cherenkov radiation, a cosmic fingerprint revealing the particle's energy and direction. These flashes are more than just data points, they're telegrams from the universe's most violent events. In 2013, IceCube made history by detecting neutrinos from outside our galaxy, some with energies 1,000,000 times greater than those produced in particle accelerators. Where did they come from? The leading suspect, supermassive black holes devouring stars, or perhaps colliding neutron stars, events so powerful they can sling particles across billions of light years without slowing them down. But here's what makes neutrinos revolutionary. They don't play by light's rules. While photons get absorbed or scattered by cosmic dust, neutrinos barrel through everything. A single neutrino could pass through a light year of lead without stopping. That means when we detect one, it's giving us a pristine, unedited snapshot of its origin, untouched by the chaos of interstellar space. It's like receiving a letter sealed at the moment of a star's death, delivered straight to our doorstep billions of years later. The future of neutrino astronomy is even more thrilling. Projects like the Pacific Ocean Neutrino Experiment, or P1, aim to turn entire ocean depths into detectors, while next-generation upgrades to IceCube will sharpen its vision tenfold. The goal, to trace neutrinos back to their sources with pinpoint accuracy, turning random flashes into a cosmic GPS. Imagine pinpointing a distant supernova not by its light, which might arrive days later, but by the neutrino pulse that races ahead at nearly light speed, giving us an early warning to train telescopes on the explosion's birth. or uncovering hidden black holes lurking behind thick veils of dust, invisible to traditional telescopes but screaming their presence through neutrino bursts. Perhaps most tantalizing is what neutrinos could reveal about the universe's most elusive puzzles. Some theories suggest certain high-energy neutrinos might be signatures of dark matter annihilation, clues to that 85% of the universe's mass we've never seen. Others speculate they could carry traces of extra dimensions or exotic particles predicted by quantum gravity. Every neutrino we catch is a cipher, and with each decode, we're not just learning about the cosmos, we're rewriting the rules of how to observe it. For centuries, astronomy meant studying light. Now, we're learning to read the universe in a language written by particles that barely acknowledge matter exists, and in their silence, they're telling us more than we ever dreamed. Supercomputers have become the ultimate cosmic laboratories, places where we can recreate the universe from scratch, tweak the laws of physics, and watch what happens. Take NASA Pleiades, a machine capable of performing quadrillions of calculations per second. It doesn't just crunch numbers, it builds entire galaxies in silico, simulating billions of years of cosmic evolution in weeks. These aren't just pretty animations, they're precision tools, testing theories against real-world observations in ways that would be impossible with telescopes alone. For example, when scientists simulate the distribution of dark matter, the resulting cosmic web, a vast filamentary structure, matches almost perfectly with the ghostly halos observed around real galaxies. It's like solving a puzzle by building the missing pieces yourself, then holding them up to the light to see if they fit. But the real magic happens when these simulations collide with the unexpected. Imagine programming a supercomputer to model the birth of a black hole, only to watch it spit out something stranger. A black hole spinning so fast it warps spacetime into a donut shape, or two supermassive black holes locked in a dance that flings stars across their galaxy like cosmic confetti. These aren't glitches, they're discoveries, virtual experiments that reveal phenomena telescopes haven't spotted yet. When the Event Horizon Telescope captured the first image of a black hole's shadow in 2019, it was simulations that helped interpret the data, showing how the black hole's spin and the surrounding plasma should distort the light. Without supercomputers, that iconic orange ring might have remained a blur of unknowns. The scale of these simulations is staggering. To model just one galaxy like our Milky Way, a supercomputer must track hundreds of billions of particles, each representing stars, gas clouds, or clumps of dark matter, all while calculating their gravitational pulls, collisions, and energy exchanges. Add supermassive black holes, magnetic fields, and cosmic rays, and the complexity explodes. Yet these virtual universes are getting so accurate, they're starting to predict real-world observations before telescopes see them. Simulations of the early universe, for instance, suggested that the first galaxies should be smaller and messier than we thought. Years later, the James Webb Space Telescope confirmed it, spotting these cosmic toddlers in the distant universe, their irregular shapes mirroring the model's predictions. What's next? As quantum computing edges closer to reality, we're on the brink of simulations so detailed they could recreate the quantum fluctuations of the Big Bang itself, or unravel the mystery of why our universe has more matter than antimatter. Some projects are even weaving artificial intelligence into the mix, training neural networks to spot patterns in simulations that humans might miss, like the faint gravitational echoes of ancient galaxy collisions. This isn't just about building better models, it's about creating a mirror universe inside our machines, one where we can run experiments on the fabric of reality itself. The cosmos has spent 13 billion years writing its history. With supercomputers, we're not just reading it, we're helping write the next chapters. There's something beautifully democratic about the night sky. It belongs to everyone, and now, thanks to the rise of citizen science, everyone can help unlock its secrets. Gone are the days when cutting-edge astronomy was confined to ivory towers and elite institutions. Today, platforms like Zooniverse have turned millions of everyday people into cosmic detectives, sifting through data that even the most advanced algorithms struggle to interpret. Take the case of Tabby's star, a bizarre flickering sun in the constellation Cygnus. When professional astronomers were baffled by its irregular dimming patterns that didn't match any known planet or dust cloud, it was volunteers on Planet Hunters, a Zooniverse project, who first flagged the anomaly. Their curiosity sparked a scientific frenzy, with theories ranging from swarms of comets to, yes, even speculative alien megastructures. While the mystery remains unsolved, one thing's certain: without those keen-eyed amateurs, this cosmic oddity might have slipped through the cracks. What's remarkable is how accessible this revolution has become. You don't need a PhD or $1 million telescope to contribute. With nothing more than a laptop, anyone can log into projects like Galaxy Zoo and help classify distant galaxies, their spiral arms or elliptical shapes providing clues to how the universe evolves. Some volunteers have spotted rare green pea galaxies, tiny, intensely star-forming systems, or even accidental supernova, their sharp eyes catching flashes of light that automated surveys missed. And when it comes to exoplanets, amateur astronomers equipped with backyard telescopes and off-the-shelf cameras are now routinely confirming NAS, a test satellite candidates, their observations filling gaps in the data that professionals simply don't have the manpower to cover. But the real game changer, the synergy between human intuition and machine learning. While AI excels at processing vast datasets, it often stumbles on irregularities, the cosmic glitches that might signal something revolutionary. That's where the crowd shines. In one striking example, volunteers sifting through Kepler telescope data identified a star with such erratic dimming that it defied all conventional explanations. Dubbed Boyajian star after the astronomer who led its study, it became a poster child for how collective curiosity can push science forward. Meanwhile, projects like SETI at home harness idle home computers to analyze radio signals for signs of extraterrestrial intelligence, turning global processing power into a virtual supercomputer. This isn't just about outsourcing grunt work. Citizen science is reshaping how discoveries happen. When a Dutch schoolteacher named Hanny van Arkel stumbled upon a strange, glowing gas cloud while classifying galaxies, astronomers didn't just pat her on the back. They named it Hanny's voorwerp, Dutch for object, and scrambled telescopes to study it. Today, we know these voorwerpen are echoes of quasar light, illuminating intergalactic ghosts. Similarly, amateur astrophotographers routinely capture Jupiter's storms or comet outbursts with gear cheaper than a smartphone, their images often rivaling professional quality. The line between amateur and expert is blurring, and the universe is richer for it. Perhaps the most profound impact of this movement isn't just the data, it's the mindset. Every time a retiree in Tokyo tags a galaxy or a teenager in Brazil clocks an exoplanet transit, they're part of something bigger, proof that science isn't a spectator sport. The cosmos has always been humanity's shared inheritance, and now, for the first time in history, we're all invited to decode it together. The next great discovery might not come from a mountaintop observatory. It could be brewing in a suburban backyard, a classroom, or a coffee shop, wherever someone looks up and wonders, what if I just checked one more star? History isn't just written in books, it's etched in the alignment of pyramids, encoded in clay tablets, and hidden in the shadows of ancient temples. For centuries, civilizations we now call lost were mapping the heavens with tools we're only beginning to understand. Take the Babylonians, who meticulously recorded the movements of Jupiter on cuneiform tablets over 2,000 years ago. At first glance, these seem like simple observations. But when modern astronomers analyzed them with spectral imaging, they found something astonishing. These ancient scholars weren't just noting positions, they were calculating Jupiter's speed using geometric principles eerily similar to calculus, a math that wouldn't be invented for another 1,500 years. Then there's the Mayan Dresden Codex, a bark paper book that survived centuries of humidity and conquest. To the untrained eye, its pages are just rows of dots and bars, Mayan numerals tracking the planet Venus. But when researchers applied multispectral imaging to faded sections, they uncovered hidden corrections, proof that Mayan astronomers were refining their predictions over generations. Their Venus tables were accurate to within 2 hours over a 500-year period, a feat requiring obsessive observation and a deep grasp of celestial mechanics. How? By turning their temples into observatories. At Chichen Itza, the Pyramid of El Castillo casts a serpentine shadow during equinoxes, a dazzling display of architecture doubling as an astronomical calendar. But here's what's truly humbling. We're realizing how much of this knowledge was shared. The Nebra Sky Disk, a 3,600-year-old bronze artifact found in Germany, depicts the Pleiades cluster alongside a golden sun and moon. Similar motifs appear in Greek, Egyptian, and Mesopotamian art, proof that Bronze Age cultures across continents were trading not just goods but cosmic ideas. Modern X-ray fluorescence scans reveal even the disk's metals came from as far as Cornwall, hinting at a sprawling network of astronomer priests who saw the sky as a common language. What's changing now is our ability to listen to these ancient voices. LiDAR technology, the same tool used to map rainforest ruins, is revealing hidden observatories, like the recently discovered supersized Stonehenge in Spain, its massive stones aligned to solstices. Meanwhile, AI is deciphering damaged texts, reconstructing star catalogs from charred Roman scrolls or water-stained Tibetan manuscripts. One algorithm even identified a forgotten supernova in a 1st century Chinese court record, matching the remnants of a modern-day nebula. This isn't just archaeology, it's time travel. When a team used 3D modeling to recreate the Antikythera mechanism, a 2,000-year-old Greek computer, they found it could predict eclipses and track the Olympic Games. Its gears, precision cut by hand, modeled the cosmos with a sophistication rivaling 18th century clocks. And in Egypt, astronomers are now convinced the Great Pyramid shafts weren't just spiritual passages, they pinpointed stars like Sirius, turning the pharaoh's tomb into a stone planetarium. The lesson: our ancestors weren't primitive stargazers, they were scientists building an understanding of the universe piece by piece, passing it down through symbols we're finally learning to read. Every time we decode an ancient star chart or reconstruct a forgotten observatory, we're not just uncovering history, we're reclaiming chapters of a story that belongs to all of humanity. The sky was their textbook, the stars their teachers, and now, with the tools of modern science, we're sitting in on those same celestial lessons, rediscovering wisdom that was written in light millennia ago. The search for life beyond Earth has always been the ultimate cosmic detective story, and now we've got our best clues yet. Imagine pointing a telescope at a distant world and not just seeing its outline but smelling its atmosphere. That's the power of modern spectrographs, instruments so precise they can split starlight filtering through an exoplanet's air into a chemical barcode. A whiff of oxygen here, a trace of methane there, these aren't just gases. They're potential signatures of something extraordinary, biology at work. Take K2-18b, a super-Earth 120 light-years away. When the James Webb Space Telescope detected water vapor, carbon dioxide, and even dimethyl sulfide, a compound only produced by life on Earth, in its skies, the discovery sent shockwaves through the scientific community. It wasn't proof of aliens, but it was something just as thrilling, a roadmap to where we should look next. This is where missions like the Habitable Worlds Observatory come in. Unlike Webb, which peers at a handful of promising planets, this next-generation telescope will be a life-hunting machine, designed to scan dozens of Earth-like worlds in their star's habitable zones, the Goldilocks regions where liquid water could exist. Its coronagraph, a high-tech starlight blocker, will work like a cosmic visor, dimming parent stars to reveal the faint glow of orbiting planets. Then, its spectrographs will go to work, analyzing atmospheres for what astrobiologists call biosignatures, chemical imbalances that scream life. Oxygen is the big one. On Earth, it's a byproduct of photosynthesis constantly replenished. Without life, it would vanish in mere millions of years. But there are other clues: methane that doesn't match volcanic activity, or bizarre combos like nitrous oxide alongside ozone. Even artificial pollutants, chlorofluorocarbons from industrial civilizations, could show up in the data. Of course, nature loves to play tricks. A lifeless planet with active geology might mimic biosignatures through underground serpentinization, a process that produces hydrogen and methane. That's why scientists are hunting for technosignatures, radio signals, laser pulses, or even megastructures like Dyson spheres. Projects like Breakthrough Listen are scanning millions of stars for patterns that can't be explained by natural phenomena, while AI sifts through the noise for anomalies. The goal isn't just to find life, it's to confirm it beyond doubt. What's truly mind-bending is the scale of this search. The Milky Way alone has an estimated 6 billion Earth-like planets. Even if only 1 in a million harbors life, that's still 6,000 living worlds. And with telescopes now capable of spotting city lights on distant exoplanets, something the Habitable Worlds Observatory could achieve, we're not just looking for microbes. We're scanning for civilizations. The implications are staggering. Finding even a single bacterium beyond Earth would prove life isn't a fluke, it's a cosmic inevitability. It would mean the universe is teeming with possibilities, that DNA, or something like it, might be as common as stardust, and if we found intelligence, that would rewrite not just science but philosophy, religion, even our identity as a species. We're no longer just asking if life exists out there. With every atmospheric scan, every radio whisper, we're narrowing the search to a single, electrifying question. Which world will answer us first? Fast radio bursts are the universe's most enigmatic Morse code, blinding flashes of energy that vanish in milliseconds, yet pack more power than the sun emits in decades. When astronomers first stumbled upon them in 2007, the discovery was so unexpected, some dismissed it as telescope static, but then they kept coming. Each one a cosmic scream from galaxies billions of light years away, defying explanation. What could possibly unleash such fury? The suspects range from collapsing neutron stars to vibrating cosmic strings, or, in the most tantalizing scenarios, something far more deliberate. Enter CHIME, the Canadian Hydrogen Intensity Mapping Experiment. This sprawling radio telescope in British Columbia looks like a half-pipe skate ramp crossed with a futuristic barn. But don't let its odd design fool you. It's revolutionized the hunt for FRBs. Unlike traditional dishes that stare at narrow patches of sky, CHIME scans the entire overhead universe daily, catching bursts others miss. Thanks to its relentless gaze, we've gone from detecting a handful of FRBs to hundreds, each one a clue etched in radio waves. Some burst once and vanish. Others, like the famous repeater FRB 1211-2, fire off sporadically like a cosmic alarm clock with no discernible pattern. The most compelling theories: magnetars, highly magnetized neutron stars spinning so fast their magnetic fields could snap like rubber bands, releasing apocalyptic energy. In 2020, astronomers caught a smoking gun, a magnetar in our own galaxy erupting with an FRB-like pulse. But here's the twist: it was thousands of times weaker than extragalactic bursts, suggesting something even more extreme lurks out there. Some models propose colliding neutron stars or black holes shredding white dwarfs. Others flirt with exotic physics, like action stars, theoretical dark matter clumps evaporating in bursts of radio light. Then there's the elephant in the room: could some FRBs be artificial? While most scientists dismiss extraterrestrial origins, the repeating burst's irregular cadence keeps the door slightly ajar. SETI researchers have scanned FRB sources for narrowband signals or patterns, finding nothing yet. But the sheer energy involved suggests that if these are messages, they're not for us. Imagine a civilization powering interstellar beacons by tapping neutron stars like cosmic batteries, a thought both humbling and thrilling. What's clear is that every new detection rewrites the playbook. When CHIME spotted an FRB originating from a globular cluster, an ancient stellar retirement home where magnetars shouldn't exist, it forced a rethink of where these bursts can form. Others trace back to spiral galaxies like our own, hinting that the conditions to create them might be more common than we imagined. The real prize: capturing an FRB's afterglow, lingering radio or X-ray emissions that could reveal its engine. Telescopes worldwide now scramble at each alert, hoping to catch a burst in multiple wavelengths like cosmic triangulation. This isn't just about solving a puzzle, it's about probing the limits of physics itself. FRBs traverse billions of light years, their signals subtly distorted by the sparse electrons between galaxies. By studying these distortions, astronomers can map the universe's missing matter, the invisible web that binds galaxies together. And if we ever find an FRB that defies all known explanations, that's when the real fun begins. These millisecond flashes are more than cosmic fireworks. They're telegrams from the edge of known physics, and with every burst, the universe drops another breadcrumb on the path to understanding. Imagine a world where the rain isn't made of water, but molten iron. That's the reality on WASP-76b, a scorching exoplanet 740 light-years away, where daytime temperatures soar above 2,400 degrees Celsius, hot enough to vaporize metals. Telescopes like the European Space Agency's CHEOPS satellite have caught the eerie glow of this iron vapor rising on the planet's permanent sunlit side, only to condense into liquid metal droplets on the frigid, tidally locked night side. It's weather straight out of a cosmic horror story, and it's just one example of how exoplanet meteorology is rewriting the rules of atmospheric science. The key to decoding these alien climates lies in a technique called phase curve analysis. By observing how a planet's brightness changes as it orbits its star, astronomers can map temperature variations across its surface, essentially creating thermal weather maps of worlds light years away. Take HD 189-733b, a cobalt blue gas giant where winds scream at 7,000 kilometers per hour, carrying clouds of silicate particles that rain glass sideways. The Hubble Space Telescope detected these supersonic storms by tracking changes in the planet's atmospheric composition during its 4-day orbits. But what's truly groundbreaking is how these observations reveal universal principles. The same physics that drives Earth's jet streams' temperature differences between hot and cold regions appears to govern winds on HD 189-733b, just on a monstrous scale. Then there's the puzzle of Kelt 9b, the hottest exoplanet known. With a dayside temperature hotter than most stars, its atmosphere is literally boiling away, leaving a comet-like tail of vaporized metals stretching into space. The James Webb Space Telescope recently caught this evaporation in action, revealing how ultraviolet radiation from the planet's host star is stripping away layers of its atmosphere at a rate of 10 million tons per second. It's a cosmic demolition derby, showing us how some planets might be doomed from birth. Yet even here there are surprises. Some ultra-hot Jupiters, like TOI 210b, defy expectations by holding onto thick atmospheres despite their infernal conditions, hinting at unseen chemical processes or magnetic fields acting as planetary force fields. What makes these discoveries more than just celestial curiosities is how they sharpen our search for habitable worlds. By studying atmospheric circulation on extreme planets, scientists are learning to spot the subtle fingerprints of milder climates. A planet with efficient heat distribution, like Earth's ocean currents, might avoid the deadly temperature swings of tidally locked worlds. Seasonal changes detected through shifting cloud patterns or atmospheric composition could point to axial tilts similar to ours, a potential stabilizer for climate. Even volcanic activity, inferred from sudden spikes in sulfur dioxide, might signal a geologically active world with carbon cycles that regulate temperatures. The ultimate goal: to find an atmosphere that's not just strange but unstable in the right way. Earth's oxygen-rich air would quickly vanish without life to replenish it. If we spot a distant world with similar chemical imbalances, methane coexisting with oxygen, or nitrous oxide spikes without volcanic sources, it could be the closest thing to a cosmic welcome sign we'll ever get. Until then, every molten iron storm and glass-spewing hurricane is teaching us one undeniable truth. When it comes to weather, the universe has a flair for the dramatic that puts our wildest imaginations to shame. Dark energy is the universe's greatest magic trick, an invisible force stretching space itself faster and faster, defying gravity's pull without leaving a trace. We know it exists because distant galaxies are racing away from us at speeds that should be impossible, their light stretched into redder, longer wavelengths like cosmic taffy. But here's the unsettling truth: we have no idea what it actually is. Is it a property of space itself, as Einstein once suggested with his cosmological constant, or something far stranger, a fluctuating field that could change strength over time, altering the fate of everything? That's the puzzle missions like Euclid are designed to solve, and the answers could rewrite not just cosmology, but our very understanding of reality. Euclid, the European Space Agency's dark energy hunter, isn't just another telescope. It's a cosmic cartographer on an unprecedented scale, set to map the precise positions and shapes of 2 billion galaxies across 10 billion light-years of space. Why shapes? Because dark energy doesn't just push galaxies apart, it warps the fabric of space-time, bending the light from distant objects like a funhouse mirror. By measuring these subtle distortions, called weak gravitational lensing, Euclid can create a 3D stress map of the universe's expansion, revealing where and how dark energy's push is strongest. But the real genius lies in its dual approach. Euclid will also use Baryon acoustic oscillations, frozen ripples from the early universe, as a cosmic ruler. These ancient sound waves, imprinted in galaxy clusters, act like mile markers, letting scientists measure expansion rates across cosmic time with pinpoint accuracy. What keeps cosmologists up at night is the possibility that dark energy isn't constant. Some theories suggest it could grow stronger, accelerating expansion until galaxies, stars, and even atoms are torn apart in a big rip. Others propose it might fade, allowing gravity to reverse the expansion in a catastrophic big crunch. Then there's the most unsettling idea of all, that dark energy is just the tip of an undiscovered physics iceberg. Modified gravity theories like MUND argue that Einstein's equations break down on cosmic scales, and what we call dark energy is actually a sign that gravity itself works differently than we thought. The stakes couldn't be higher. If Euclid or its successor, NASA's Nancy Grace Roman telescope, find evidence that dark energy varies, it would mean the universe's expansion isn't just speeding up, it's unpredictable. A force that grows stronger over time could eventually rip apart spacetime's fabric, ending reality as we know it. Conversely, if it's constant, we might face a quieter but equally bleak future. A heat death where galaxies vanish over the horizon, leaving isolated stars to burn out in an ever colder void. Yet for all the existential dread, there's profound beauty in this quest. Euclid's maps won't just chart dark energy, they'll reveal the universe's skeleton, the vast cosmic web where galaxies cluster along filaments of dark matter, tracing patterns laid down in the Big Bang's first moments. By comparing these structures across cosmic epochs, we're essentially watching the universe grow up, from its turbulent infancy to its mysterious, accelerating adulthood. Dark energy may be the ultimate cosmic villain, but it's also the key to understanding the grandest story of all, how everything began and how it might one day end. And with every galaxy Euclid catalogues, we're not just observers of that story, we're turning the pages. Asteroids have always been the solar system's forgotten treasure chests, rocky remnants from the dawn of our cosmic neighborhood, drifting silently through the void. But now we're learning they're far more than relics. They could be the gas stations, construction yards, and even life support systems for humanity's next giant leap into space. Take water, for example, locked within certain asteroids as ice. It's not just a resource, it's a cosmic Swiss Army knife. Split into hydrogen and oxygen, it becomes rocket fuel. Keep it liquid and it's drinking water for astronauts. Shielded from sunlight, these frozen reservoirs could have survived untouched for billions of years, waiting for us to tap them. And that's just the beginning. Metals like platinum, nickel, and cobalt, abundant in metallic asteroids, could be harvested to build habitats or spacecraft in orbit, bypassing the colossal cost of launching materials from Earth's gravity well. This isn't science fiction. Companies like Planetary Resources and Deep Space Industries, backed by billionaires and NASA contracts, are already deploying telescopes equipped with advanced spectrometers to scan near-Earth asteroids for these precious commodities. These instruments don't just spot asteroids, they analyze their composition from afar by studying how sunlight reflects off their surfaces. Each mineral and metal leaves a unique fingerprint in the light, allowing scouts to pinpoint the most valuable targets before a single robot is launched. The frontrunners, C-type asteroids, rich in carbon and water, and M-types, packed with enough metal to dwarf Earth's entire platinum reserves. But identifying these cosmic gold mines is only step one. The real challenge lies in extraction. Imagine a robotic miner, no larger than a refrigerator, landing on an asteroid where gravity is so weak, a sneeze could send you drifting into space. Traditional drills and shovels are useless here. Instead, prototypes are testing wild solutions like using concentrated sunlight to vaporize water ice, then capturing the steam, or deploying nanobot swarms to chemically leach metals from rubble. NASA OSIRIS-REx mission gave us a sneak peek of the technique when it grabbed a sample from asteroid Bennu in 2020, using a puff of nitrogen gas to stir up loose material like a cosmic vacuum cleaner. Future missions aim to scale this up, with drills that anchor to the surface using harpoons or even synthetic gecko grip adhesive inspired by the sticky feet of lizards. The implications are staggering. A single water-rich asteroid could fuel thousands of deep space missions, turning the Moon or Mars into hubs for refueling rather than dead-end destinations. And metals mined in space wouldn't just save launch costs, they'd revolutionize manufacturing. In microgravity, molten metals can be 3D printed into structures impossible to forge on Earth, like ultra-lightweight solar sails or sprawling space station components. Some visionaries even dream of asteroid-derived materials building orbital solar farms, beaming clean energy back to Earth. Yet for all the economic potential, the true value of asteroid mining isn't measured in dollars. It's about resilience. Every ounce of water or fuel harvested off-world makes humanity less dependent on our fragile planet. Imagine a future where lunar bases refuel from asteroid ice, or where Mars colonists recycle metals from passing space rocks. Suddenly, the solar system stops being a series of isolated outposts and becomes an interconnected web of resources, sustaining life far beyond Earth. The asteroids drifting overhead aren't just rocks, they're stepping stones, and we're just beginning to learn how to walk. The idea of wormholes sounds like pure science fiction, a cosmic subway system linking distant corners of the universe through tunnels in spacetime. Yet the equations of general relativity don't just allow for their existence, they practically tease us with the possibility. Picture a black hole's intense gravity not as a one-way street, but as a bridge folded back on itself, connecting two points that might otherwise be billions of light years apart. For decades, this remained a mathematician's daydream, but today, with tools like LIGO and the upcoming LISA mission, we're closer than ever to turning speculation into testable science. The hunt begins with gravity itself. Wormholes, if they exist, would warp spacetime in unique ways, leaving gravitational fingerprints unlike black holes or neutron stars. Theorists predict their mouths might produce rhythmic ripples in spacetime as they breathe, a signature future detectors could spot. Others suggest that matter passing through a wormhole would create bizarre echoes in gravitational wave signals, like hearing a shout reverberate through a tunnel. The challenge: these signals would be vanishingly faint, buried in cosmic noise. That's where AI comes in. Machine learning algorithms are now trained to sift through gravitational wave data for anomalies, hunting for patterns no human would recognize. A single detection could rewrite the rules of physics overnight, but finding a wormhole is only half the battle. The real question is, could we ever use one? Traversable wormholes, as envisioned by physicists like Kip Thorne, would require exotic matter with negative energy to prop them open, something we've only glimpsed in quantum experiments like the Casimir effect. Even then, the engineering challenges are mind-bending. A stable wormhole might need the mass energy of a star compressed into a structure thinner than an atom, held open by forces we can barely imagine. Yet here's the tantalizing part. If we cracked it, the payoff would dwarf the Apollo program. A wormhole network could turn interstellar travel into a commute, linking colonies across the galaxy without breaking light speed. Of course, nature might have other plans. Some theories suggest wormholes are inherently unstable, snapping shut the instant anything enters. Others argue they're more like cosmic mirages, mathematical quirks with no physical reality. But the mere possibility has sparked wild yet serious proposals. NASA's Innovative Advanced Concepts program once funded a study on negative energy propulsion, while physicists at Stanford have modeled how quantum entanglement might someday stabilize microscopic wormholes. It's a long shot, but so was splitting the atom until it wasn't. What makes this search so thrilling isn't just the far future potential. It's the way wormholes force us to rethink space itself. Every time a gravitational wave detector picks up an unexplained ripple, every time quantum experiments hint at negative energy, we're not just testing equations. We're probing whether the universe left backdoors in its code, and if we're clever enough to find them. For now, wormholes remain the ultimate cosmic what if. But in a universe full of surprises, betting against them might be the riskiest move of all. Cosmic rays are the universe's ultimate mystery, bullet subatomic particles hurtling through space at nearly light speed, packing enough energy to rival a major league fastball. They rain down on Earth constantly, tens of thousands every second, yet their origins have been one of astrophysics' most stubborn puzzles for over a century. Some come from our sun, but the real enigmas are the ultra-high-energy cosmic rays, particles so powerful, their kinetic energy dwarfs anything human-made accelerators can produce. Where does this celestial artillery come from? The suspects range from supernova shockwaves to spinning neutron stars, but the smoking guns have been frustratingly elusive until now. Enter the Cherenkov Telescope Array, or CTA, a next-generation observatory spread across 2 continents. Unlike traditional telescopes that capture light, the CTA hunts for the faint blue flashes created when cosmic rays slam into Earth's atmosphere. These flashes, called Cherenkov radiation, last just nanoseconds, but they're packed with clues. By analyzing their brightness and angle, scientists can trace the particles' paths back through interstellar space like cosmic breadcrumbs. Already, the CTA has linked some cosmic rays to the remnants of supernova stellar explosions so violent, they act as natural particle accelerators. But here's the twist. The highest energy rays don't match known supernova. Their trajectories point to something even more extreme: active galactic nuclei, where supermassive black holes spew jets of plasma stretching millions of light years, or perhaps colliding galaxy clusters, where magnetic fields twist and snap like cosmic rubber bands, flinging particles across the universe. The implications go far beyond astrophysics. Cosmic rays have been shaping our planet since its birth. When these particles strike Earth's atmosphere, they trigger cascades of secondary particles that seed cloud formation and even influence lightning rates. Some theories suggest they played a role in life's evolution by causing genetic mutations that drove biodiversity. On Mars, where a thin atmosphere offers little protection, cosmic rays may have stripped away conditions needed for life. Even space travel hinges on this puzzle. Astronauts outside Earth's magnetic shield risk exposure to these microscopic bullets, with potential effects ranging from cancer to cognitive decline. Understanding their origins isn't just about mapping the universe, it's about safeguarding our future in it. What makes this hunt so electrifying is how it bridges scales. A single cosmic ray, smaller than an atom, can carry the energy of a falling brick, a paradox that defies classical physics. To unravel it, scientists are turning the atmosphere itself into a detector. Projects like the Pierre Auger Observatory in Argentina use thousands of water tanks to catch the particle showers spawned by cosmic rays, while space-based detectors like the Alpha Magnetic Spectrometer on the ISS snag the rays before they hit the atmosphere. Together, they're piecing together a map of the universe's most powerful accelerators, and each new discovery reveals how much we've underestimated nature's ability to hurl matter across the cosmos. The real surprise: some cosmic rays might not be particles at all. Theories suggest a fraction could be strangelets, hypothetical nuggets of strange quark matter left over from the Big Bang. These would shatter our understanding of nuclear physics, proving that matter can exist in forms utterly alien to our experience. Others might be neutrinos in disguise, or even signatures of dark matter annihilation. Every time a detector catches an ultra-high-energy ray, it's not just solving a mystery, it's testing the boundaries of known physics. The universe has been firing these cosmic bullets at us for eons. Now, with tools like the CTA, we're finally learning to read the fingerprints on the trigger. The universe is unimaginably vast, with billions of galaxies, each containing billions of stars. So where is everybody? That's the haunting question at the heart of Fermi's paradox, the eerie contradiction between the high probability of alien civilizations and the deafening silence we hear in return. Statistically, the numbers are on Extraterrestrial's side, with over 5,000 exoplanets discovered in our galactic backyard alone, and trillions more likely dotting the cosmos. The odds of life emerging elsewhere seem overwhelming. Yet after decades of listening, scanning, and searching, we've found nothing but static. No signals, no artifacts, not even a single microbial fossil beyond Earth. It's as if the universe built a playground for life, then left it empty. But here's the twist. Our tools for eavesdropping on the cosmos are finally catching up to the enormity of the question. SETI laser-based optical searches now scan for pulsed light signals, brief, intentional flashes that could cut through interstellar noise like a cosmic lighthouse. Unlike radio waves which disperse over distance, laser pulses stay tightly focused, making them ideal for targeted interstellar hello messages. Meanwhile, projects like Breakthrough Listen are turning radio telescopes into galactic eavesdroppers, sifting through millions of frequencies at once with AI capable of spotting patterns no human could recognize. In just the past few years, these efforts have flagged intriguing anomalies like the infamous WOW signal successor, BLC-1, a narrowband radio burst that seemed artificial before being traced to earthly interference. Yet the search isn't limited to deliberate signals. Astrobiologists are hunting biosignatures, chemical imbalances in exoplanet atmospheres that scream life. Oxygen, methane, even industrial pollutants like chlorofluorocarbons could hint at civilizations altering their worlds. The James Webb Space Telescope is already analyzing distant skies for these fingerprints, while future missions like Europe's Ariel will specialize in sniffing out alien air. But what if we're looking for the wrong things? Some theorists argue advanced civilizations might abandon radio for quantum communication or neutrino beams, leaving no trace we'd recognize. Others suggest they could harness entire stars with Dyson spheres, their energy-harvesting megastructures detectable as unnatural infrared glows, something surveys like Gaia are now scanning for. The explanations for the great silence range from sobering to spine-chilling. Maybe life is vanishingly rare and Earth is a cosmic fluke, or perhaps civilizations inevitably self-destruct, their lifespans too short to overlap with others. There's the zoo hypothesis, the idea that aliens deliberately avoid contact, observing us like a galactic nature preserve. More unsettling are scenarios where predatory civilizations force others into radio silence, or where AI-dominated societies lose interest in physical exploration. Even our own history offers clues. When European ships reached remote Pacific islands, indigenous cultures often didn't notice until it was too late. Could we be the unwitting islanders of the Milky Way, oblivious to a galactic conversation happening just beyond our perception? What's clear is that the silence isn't passive, it's a mirror reflecting our assumptions back at us. Every time we tune a radio dish or analyze an atmospheric spectrum, we're not just searching for aliens, we're testing what it means to be a civilization, how long intelligence might endure, and whether the universe favors life or loneliness. The answer to Fermi's paradox won't just tell us if we're alone. It'll reveal whether the cosmos is a thriving network of minds or an unimaginably vast stage with only one actor. And with every new telescope, algorithm, and interstellar probe, we're pulling back the curtain a little further, one silent, starry inch at a time. For centuries, astronomy was like flipping through a photo album, static snapshots of a universe frozen in time. But now, we've traded those still images for a high-definition live stream of the cosmos in motion. Time-domain astronomy has flung open a new window, revealing a universe that crackles with change, stars that flare to life and vanish in weeks, black holes that shred passing stars in violent tidal disruptions, and neutron stars colliding in bursts of gold-forging fury. This isn't your grandparents' night sky anymore, it's a cosmic blockbuster playing out in real time, and we've finally got front row seats. At the heart of this revolution is the Vera C. Rubin Observatory, a game-changing telescope poised to scan the entire visible sky every 3 nights with a camera the size of a small car. Imagine a celestial motion detector so sensitive it can spot a flickering candle on the moon. Over a decade, Rubin will catch tens of millions of transient events, supernova blinking into existence, asteroids tumbling through the void, even mysterious fast blue optical transients that defy explanation. But here's what's truly groundbreaking. The moment Rubin detects something unusual, it triggers a global alert, sending coordinates to telescopes worldwide within seconds. Gone are the days when astronomers missed a supernova's critical early hours because no one was looking at the right patch of sky. Now, we're watching the universe's drama unfold scene by scene, like detectives piecing together a cosmic crime in progress. Take the case of a 2018 cow, a bizarre flare spotted in 2018. Within hours of detection, telescopes across 7 continents swung into action, capturing its light across radio, X-ray, and ultraviolet wavelengths. What they witnessed was unprecedented, a star being torn apart by a black hole, its debris swirling into a glowing disk hotter than the sun. But the real surprise came weeks later, when the flare suddenly reignited, as if the black hole had belched back part of its meal. Without time-domain astronomy's rapid response, we'd have missed this critical clue to how black holes feed and grow. Yet Rubin is just the beginning. Networks like the Zwicky Transient Facility and the All-Sky Automated Survey for Supernova are already turning up oddities that challenge our understanding. Some transients brighten and fade too fast to be supernova, like luminous red nova, thought to be stars merging in a fiery embrace. Others, like repeating fast radio bursts, flicker with clockwork precision, hinting at neutron stars with magnetic fields so intense they warp spacetime itself. Each discovery is a puzzle piece, revealing how matter behaves under extremes impossible to replicate on Earth. What makes this era so thrilling isn't just the volume of data, it's the collaborations it sparks. When a gravitational wave detector like LIGO senses a ripple from colliding neutron stars, time-domain telescopes race to pinpoint the afterglow, combining gravity and light to tell the full story. Citizen scientists sift through alerts, spotting anomalies professional astronomers might overlook. Even AI plays a role, training on past transients to predict what new flares might mean, like the supernova that erupted with a double peak, suggesting a star had swallowed its binary companion before exploding. We're witnessing the birth of a new kind of astronomy, one where the sky isn't just studied, but surveilled. No longer confined to snapshots, we're compiling a cinematic record of the universe's most fleeting moments, from the birth cries of black holes to the death throes of ancient stars. Every flicker, every flare is a message in a bottle, tossed into the cosmic ocean with a single line. Pay attention, something extraordinary is happening right now. And for the first time in history, we're there to catch it. What if our universe isn't the only one? Imagine a cosmic tapestry where countless other realities exist alongside ours, each with its own laws of physics, stars, and even versions of you making different choices. This isn't just the stuff of science fiction. The multiverse hypothesis, once relegated to philosophical debates, is now a legitimate frontier of scientific exploration. And while we can't yet step into an alternate dimension, strange anomalies in our own universe might be whispering tantalizing clues. Take the cosmic microwave background, the afterglow of the Big Bang. When scientists mapped this faint radiation, they spotted something bizarre, a mysterious cold spot spanning billions of light years where the temperature dips unexpectedly. One theory, it could be a bruise left by a collision with another universe in the distant past, a cosmic fender bender imprinted on space-time itself. Then there's quantum mechanics, where particles behave in ways that defy logic, existing in multiple states until observed. Some interpretations suggest these aren't just quirks, but glimpses into parallel realities branching off with every quantum decision. Experiments with superconducting qubits have even shown particles influencing each other across distances instantaneously, as if entangled not just across space, but across unseen dimensions. The search for proof is pushing technology to its limits. Future gravitational wave detectors, like the proposed Big Bang Observer, could hunt for ripples from universe-sized events beyond our own. Particle colliders might uncover hidden dimensions by spotting particles that briefly disappear into other realms. Even tabletop experiments with ultra-cold atoms are testing whether gravity leaks into adjacent universes, subtly altering how matter behaves on tiny scales. But the real revolution isn't just in the science, it's in what the multiverse would mean for us. If countless versions of Earth exist, does that make life inevitable or our choices meaningless? Could civilizations in other universes have cracked problems we're still struggling with? The multiverse blurs the line between physics and philosophy, forcing us to confront questions we've only dared to ask in stories. For now, it remains the ultimate what if. But with every anomaly we uncover and every experiment we design, we're not just exploring the universe, we're probing the very boundaries of reality itself. Galaxies are the universe's grandest masterpieces, spiraling whirlpools of stars, dust, and dark matter that stretch across unfathomable distances. But how do these cosmic giants grow from the faintest wisps of primordial gas into the majestic structures we see today? The answer lies in the universe's infancy, a time so distant that even light from those early moments has been stretched into the infrared by the expansion of space. That's where the James Webb Space Telescope comes in. With its unparalleled infrared vision, JWST isn't just observing distant galaxies, it's time traveling to their birth, capturing snapshots of the universe when it was a mere 5% of its current age. And what it's finding is turning decades of galaxy formation theories on their heads. Take the case of Sears 93,316, a galaxy so ancient its light has taken over 13 billion years to reach us. According to traditional models, galaxies this early in the universe's history should be small, chaotic, and barely formed, cosmic toddlers stumbling through the dark. Instead, JWST revealed a fully fledged, disk-shaped galaxy with a structure as refined as the Milky Way's, existing at a time when the universe was only 250 million years old. It's like finding a perfectly baked loaf of bread in an oven that's barely warmed up. This discovery, along with dozens of others like it, suggests that galaxies matured far faster than anyone predicted, compressing billions of years of evolution into a cosmic blink. But how? The secret might lie in the universe's earliest stars, monstrous, short-lived behemoths called population 3 stars. Unlike modern stars, which are seeded with heavier elements from previous generations, these primordial giants were made purely of hydrogen and helium, burning fiercely and dying young in spectacular supernova. Their violent deaths would have seeded the cosmos with heavier elements, triggering rapid star formation and giving nascent galaxies a head start. JWST spectral analyzers have already spotted the chemical fingerprints of these early supernovae in distant galaxies, offering the first direct evidence that population 3 stars weren't just theoretical, they were the universe's first architects. Yet stars alone don't explain everything. Galaxies are also shaped by the invisible scaffolding of dark matter, whose gravity pulls gas into dense clumps where stars can form. Supercomputer simulations, like those run on NASA Pleiades, show how dark matter halos act as cosmic nurseries, guiding gas into swirling disks or elliptical blobs. But here's the twist. JWST observations of early galaxies reveal they're far more clumpy and irregular than simulations predicted, suggesting dark matter's role might be more dynamic than we thought. Some galaxies even appear to be forming stars in frenzied bursts, as if something, perhaps collisions with other protogalaxies, shook them into action. The real breakthrough comes when simulations and observations collide. By feeding JWST data into supercomputers, astronomers are creating digital universes where they can tweak variables, dark matter density, star formation rates, even the intensity of ultraviolet radiation from early quasars, to see which combinations match reality. One recent simulation, dubbed Santiago, managed to recreate the bizarre diversity of JWST Galaxy Hall by factoring in something unexpected. Torrential gas flows from the cosmic web. These rivers of cold gas streaming along filaments of dark matter might have funneled fuel into young galaxies at breakneck speeds, jump-starting their growth in ways we're only beginning to grasp. Every new observation adds another piece to the puzzle. Some early galaxies are so massive they shouldn't exist under current physics, while others are mysteriously devoid of heavy elements despite their age. There are even hints of supermassive black holes forming alongside their host galaxies, not after a cosmic chicken and egg problem that could rewrite our understanding of how galaxies and black holes co-evolve. The more we learn, the clearer it becomes. Galaxy formation isn't a single process, but a symphony of interactions between stars, gas, dark matter, and black holes, each playing its part in shaping the universe's grand design. What's thrilling is that we're not just passive observers of this story, we're active participants, refining theories with every new data point. JWST infrared eyes, combined with supercomputers' brute force calculations, are turning galaxy formation from a static chapter in a textbook into a living, breathing field where surprises lurk around every corner. The universe didn't just build galaxies, it experimented, iterated, and sometimes broke its own rules. And now, for the first time, we're catching it in the act. 22nd breakthrough. The universe's tiniest ghosts might be hiding in plain sight. Primordial black holes, hypothetical relics from the Big Bang's first chaotic moments, could be drifting through our galaxy right now, invisible yet rewriting the rules of cosmology. Unlike the colossal black holes we've imaged at galaxy centers, these ancient leftovers would be as small as an atom but as massive as a mountain, forged in the furnace of the early universe's extreme densities. Their existence isn't just a curiosity, it could solve two of astronomy's biggest mysteries at once: the nature of dark matter and the universe's birth pangs. The hunt for these cosmic specks hinges on their unique fingerprints. Since they don't emit light, traditional telescopes are useless, but their gravity. That's another story. Imagine a primordial black hole passing between Earth and a distant star. Like a cosmic magnifying glass, its gravity would bend the star's light, causing a brief but measurable brightening, an effect called microlensing. Projects like the Optical Gravitational Lensing Experiment, or OGLE, have scanned millions of stars for these telltale flashes, narrowing down how many primordial black holes could lurk in our cosmic neighborhood. The results so far, intriguing but inconclusive, leaving the door wide open for smaller or rarer black holes to still be out there. Then there's Hawking radiation, the faint glow theorized to leak from black holes as they evaporate. For a primordial black hole nearing the end of its lifespan, this radiation could manifest as a burst of gamma rays or antimatter particles. Telescopes like NASA's Fermi Gamma-Ray Space Telescope have scoured the sky for these explosive goodbyes, but the signals are elusive, drowned out by the universe's background noise. That's where next-gen detectors come in. Proposed missions like the Gamma-Ray Burst Polarimeter aim to filter out cosmic static, tuning in to the specific frequencies where evaporating black holes might scream their last. What makes this search so electrifying is the stakes. If primordial black holes exist, they could account for some or even all of dark matter. No exotic particles required, just these ancient gravitational traps left over from the universe's first second. Their size distribution would also be a time capsule, preserving details about the conditions during cosmic inflation, that split second when the universe expanded faster than light. Some theories even suggest these black holes could be seeds for the supermassive monsters we see today, having gorged on gas and stars over billions of years. But the real game changer, their potential to unveil quantum gravity. At their microscopic scale, quantum effects and gravity collide, creating a laboratory for physics we can't replicate on Earth. Detecting Hawking radiation from a vanishing black hole would be smoking gun proof of this elusive union, bridging Einstein's relativity with the quantum realm. It's a long shot, but as detectors grow more sensitive and simulations more precise, we're closing in on these ghostly relics. The universe's smallest black holes might hold its biggest secrets, and we're just beginning to shine a light where no telescope has peered before. 23rd breakthrough, the golden age of space telescopes isn't ending with the James Webb Space Telescope. It's just getting started. Imagine instruments so advanced they could map the swirling storms on distant gas giants, or zoom in on the fiery disks where planets are born with enough detail to spot moon-forming clumps. That's the promise of next-generation observatories like the Origin Space Telescope and Lynx X-ray Observatory, each designed to push the boundaries of what we can see, hear, and even smell in the cosmos. Take Origins, slated for the 2040s. While JWST revolutionized infrared astronomy, Origins will go further, peering into the far infrared spectrum, a realm invisible to current telescopes. This is the universe's hidden language, emitted by cold dust clouds where stars are cradled and water molecules cling to interstellar grains. Origin's sensitivity will be staggering. It could detect the heat signature of a single bumblebee on Pluto, or trace water vapor in the atmospheres of exoplanets smaller than Earth. But the real magic lies in its ability to study the great cold of space regions where temperatures hover just a few degrees above absolute zero. These frigid zones hold the raw ingredients of life, complex organic molecules like ethanol and formaldehyde, floating in the void like cosmic brewing kits. Origins won't just spot them, it'll decode their chemical recipes, revealing how the building blocks of biology scatter across the galaxy. Then there's Lynx, the X-ray hunter poised to unveil the universe's most violent dramas. Where JWST sees the glow of newborn stars, Lynx will capture the death throes of matter spiraling into black holes, heated to millions of degrees. Its resolution will be 50 times sharper than Chandra's, sharp enough to trace the magnetic fields twisting around supermassive black holes or spot the X-ray flicker of a neutron star's surface quakes. One of its wildest targets, the hypothesized orphan black holes, rogue remnants of dead stars, drifting unseen through space until Lynx catches their faint X-ray whispers as they snack on interstellar gas. But the future isn't just about bigger mirrors or sharper sensors. It's about synergy. The Habitable Worlds Observatory, NAS, a next flagship after Origins, will combine ultraviolet, optical, and infrared vision to hunt for life-friendly planets. Its coronagraph will block starlight so precisely, it could reveal continents and clouds on Earth-sized worlds, or even city lights if they exist. Meanwhile, the proposed interferometer for cosmic dawn would link multiple telescopes in space to simulate a mirror the size of Earth, capturing the faint radio hum of the universe's first stars flickering to life. What ties these missions together is ambition, not just to observe the cosmos, but to interrogate it. Origins might settle whether Europa's geysers spray life's ingredients into space. Lynx could catch a black hole mid-meal, testing if Einstein's gravity holds true in extreme environments, and future telescopes might even spot technosignatures, pollution, or megastructures hinting at civilizations far older than ours. The best views aren't just coming, they're coming with questions we haven't even thought to ask yet. The universe has spent billions of years hiding its secrets. With these telescopes, we're finally learning how to look. SpaceX's reusable Falcon rockets didn't just change the economics of spaceflight, they shattered them. When the first booster landed vertically in 2015, it wasn't just a technical marvel. It was the starting gun for a new era where reaching orbit became 10 times cheaper than traditional government launches. Suddenly, universities could afford to send student-built satellites to space. Startups could deploy constellations of internet-beaming CubeSats. Even NASA, long reliant on costly one-use rockets, pivoted to booking rides on private spacecraft, freeing up budgets for ambitious missions like Artemis. This isn't merely competition, it's a reinvention of how humanity accesses the cosmos, and it's happening at breakneck speed. Blue Origin's New Glenn and Relativity Space's 3D printed Terran rockets are pushing the envelope further, promising to slash costs again by scaling up reusability and manufacturing efficiency. But the real game changer, Starship, SpaceX's towering stainless steel behemoth, designed to carry 100 metric tons to Mars for less than the price of a single space shuttle launch, could turn interplanetary travel from a once-in-a-generation event into something approaching routine. Picture a future where lunar bases resupply via Starship tankers, or where telescopes the size of football fields too massive for traditional rockets are assembled in orbit like cosmic Lego sets. The implications are staggering. Private companies aren't just supporting science, they're redefining what's scientifically possible. Beyond rockets, private ventures are democratizing access to space in ways governments never could. Companies like Astrobotic and Intuitive Machines are building lunar landers to deliver payloads for universities and artists alongside NASA instruments. The upcoming Orbital Reef, a commercial space station backed by Blue Origin and Sierra Space, will host researchers, tourists, and even filmmakers in low Earth orbit, creating a marketplace where microgravity experiments aren't reserved for elite astronauts. Even telescopes are going private. The upcoming Polaris program's Dragon missions will deploy free-flying observatories accessible via subscription, letting astronomers worldwide book time without waiting years for Hubble or Webb access. Critics argue this profit-driven model risks prioritizing spectacle over science, pointing to billionaire vanity projects like Dear Moon's lunar tourism mission. But the data tells a different story. SpaceX's Transporter rideshare program has launched over 1,000 small satellites since 2021, many for climate monitoring or disaster response. Rocket Lab's recovered electron boosters are now relanding with sensitive biological experiments intact, proving reuse doesn't compromise precision. And when NASA Psyche mission needed a ride to a metal-rich asteroid, it was SpaceX. not the agency's own SLS that offered the fastest, cheapest path. The most transformative shift might be cultural. Private companies operate with Silicon Valley's fail fast, iterate faster ethos, a stark contrast to the risk-averse bureaucracy of traditional space agencies. When SpaceX's early Falcon prototypes exploded, they streamed the failures live, then incorporated lessons into the next design within weeks. This agility has birthed innovations like satellite-to-cell phone connectivity and rapidly deployable orbital debris trackers, tools that protect both science and commerce in space. Meanwhile, startups like Axiom Space are proving space stations can turn a profit by manufacturing next-gen pharmaceuticals in microgravity, funding further exploration without taxpayer dollars. What's unfolding is a virtuous cycle. Cheaper launches enable more missions, which drive technological advances that further reduce costs. Lunar mining trials by companies like iSpace could someday provide fuel and materials for deep space missions, while asteroid prospectors like Planetary Resources aim to turn space resources into sustainable infrastructure. The line between exploration and enterprise is blurring, and the beneficiaries aren't just corporations, they're every researcher, artist, and dreamer who now has a shot at touching the cosmos. The stars have always belonged to everyone. Thanks to private spaceflight, they're finally within reach. Quantum entanglement is one of the universe's strangest parlor tricks, a phenomenon so bizarre even Einstein called it spooky action at a distance. Picture two particles born from the same quantum event, forever linked no matter how far apart they drift. Change the spin of one, and its partner instantly mirrors that change, as if information has leapt across space faster than light. For decades, this remained a lab curiosity, confined to controlled experiments spanning mere meters. Then came China's MISHUS satellite, a quantum pioneer orbiting Earth with a singular mission: to stretch entanglement to its cosmic limits. Launched in 2016, MISHUS didn't just break records, it shattered our understanding of quantum mechanics' reach. From space, it fired pairs of entangled photons to ground stations over 1,200 kilometers apart, a distance so vast any classical signal would take 4 milliseconds to bridge. Yet when scientists measured the photons' properties, they remained perfectly synchronized, as if no space separated them at all. This wasn't just proof that entanglement defies distance. It was a glimpse of a future where quantum links could weave a web across the solar system. But here's where it gets even wilder. MISHUS didn't stop at proving entanglement's reach. It demonstrated quantum teleportation, beaming the quantum state of a photon from orbit to Earth without physically transferring the particle itself. Think of it like emailing a snowflake's exact structure without moving the ice, a feat that could revolutionize secure communication. Why? Because quantum teleportation isn't just fast, it's unhackable. Any attempt to intercept the signal would collapse the quantum state, leaving eavesdroppers with gibberish and alerting the sender. Governments and banks are already eyeing this for ultra-secure networks, but the real prize lies beyond Earth. Imagine a quantum internet spanning Mars bases and lunar outposts, where astronauts transmit data instantaneously across millions of kilometers, unhindered by light speed delays. Or probes navigating the asteroid belt with entangled sensors, their measurements perfectly synchronized despite being scattered across the void. Even interstellar travel gets a rethink. While we can't teleport matter yet, entangled particles could act as cosmic Rosetta Stones, helping future AIs interpret signals from probes light years away without lag. Of course, the hurdles are as vast as the potential. Entangled photons are fragile. A single dust particle or atmospheric ripple can break their link. MISHUS only worked because space offers a near-perfect vacuum, but extending this to planets with atmospheres like Mars will require relays or quantum repeaters yet to be invented. Then there's the fundamental mystery: how does entanglement work? Some theories suggest particles tap into hidden dimensions, or that the universe itself is a hologram, with entanglement revealing its underlying code. Others propose it's evidence of a deeper, non-local reality where separation is an illusion. What's certain is that quantum entanglement isn't just rewriting the rules of communication, it's challenging our very notion of reality. Every time MISHUS or its successors forge another quantum link across the cosmos, they're not just testing physics. They're probing whether the universe is far more connected, far stranger than we ever dared to dream. And the answers they find might not just change how we talk to the stars, they could reveal that the stars have been talking back all along, in a language woven into the fabric of space itself. The universe operates by two rulebooks, and they couldn't be more different. Down in the quantum realm, particles pop in and out of existence, teleport through barriers, and exist in multiple states at once. Up at cosmic scales, gravity sculpts galaxies and black holes with predictable, elegant curves. For over a century, these two frameworks, quantum mechanics and general relativity, have refused to play nice, creating a schism at the heart of physics. But hidden in the chaos of colliding black holes and the whispers of subatomic particles, clues are emerging that might finally stitch these disjointed theories into a single, unified tapestry. Take black holes, those cosmic paradoxes where both quantum weirdness and gravitational might reach their extremes. When the Event Horizon Telescope captured the first image of a black hole's shadow in 2019, it didn't just confirm Einstein's predictions, it spotlighted a glaring contradiction. Quantum theory insists information can't be destroyed, yet black holes seemingly vaporize it forever. This information paradox has physicists scrambling for solutions, from Hawking radiation carrying scrambled data to wild ideas like firewalls at the event horizon. The key to cracking it, a theory that marries quantum mechanics' uncertainty with relativity's smooth spacetime, a framework where the rules don't break down at the edge of a singularity. Gravitational wave detectors like LIGO are another battleground for unification. When two black holes spiral into each other, their merger emits ripples in spacetime packed with secrets. Subtle anomalies in these waves, echoes, frequency shifts, or unexpected damping, could betray quantum effects warping gravity itself. Some theories predict spacetime isn't continuous but pixelated at the tiniest scales, like a cosmic digital image. If LIGO or its successor, the Einstein telescope, catches hints of this graininess, it would be the smoking gun for theories like loop quantum gravity, where spacetime is woven from indivisible threads. Then there's the particle smasher approach. CERN Large Hadron Collider doesn't just hunt for new particles. It recreates conditions last seen a trillionth of a second after the Big Bang, probing energies where quantum and gravitational forces might finally shake hands. Supersymmetry, string theory's flashier cousin, predicts a shadowy twin for every known particle, a symmetry that could smooth over the math between quantum fields and spacetime curvature. While no sparticles have appeared yet, anomalies in proton collisions or rare decays keep theorists glued to the data, searching for statistical blips that might rewrite the rules. The most tantalizing hints, though, come from the cosmos itself. The James Webb Space Telescope's deep field images reveal galaxies too mature for their age, challenging our timeline of cosmic evolution. Could this be evidence of quantum fluctuations in the early universe imprinting on galactic structures? Meanwhile, pulsars, spinning neutron stars acting as cosmic lighthouses, keep time with atomic clock precision. Minute deviations in their ticks might reveal how gravity dances with quantum spin, a subtle interaction predicted by nascent theories like asymptotically safe gravity. What makes this search so electrifying isn't just the intellectual payoff, it's the tools transforming it from philosophy to testable science. Quantum computers now simulate black hole entanglement in hours instead of millennia. AI sifts through petabytes of collider data for patterns no human could spot. Even tabletop experiments with supercooled atoms are testing whether gravity emerges from quantum entanglement, like a hologram projected from lower dimensional code. The stakes couldn't be higher. A successful theory of everything wouldn't just fill textbooks, it would redefine reality. Imagine engineering space-time wormholes using quantum loopholes, or harnessing vacuum energy from particles flickering in and out of existence. More profoundly, it would answer whether the universe is fundamentally random or deterministic, finite or infinite, alone or one of many. Every unexplained anomaly, from dark energies pushed to the muon particle's odd magnetic wobble, is a potential thread in this grand tapestry. And with each technological leap, we're not just pulling at those threads, we're starting to weave them together. Space exploration isn't just about what we can do, it's about what we should do. As rockets land on Mars and probes dive into Europa's icy oceans, we're no longer passive observers of the cosmos. We're actors capable of altering worlds we barely understand. Take the recent debate over lunar mining. Companies like iSpace aim to extract water ice from the moon's poles, a resource vital for future bases. But what if those shadowy craters, untouched by sunlight for billions of years, harbor fragile chemistry or even microbial life? The Outer Space Treaty of 1967 declares celestial bodies the province of all mankind, but it's silent on whether drilling into them could erase scientific treasures before we recognize their value. This tension between progress and preservation isn't theoretical. When NASA Perseverance rover landed on Mars, it sterilized its components to avoid contaminating the red planet with Earth microbes. Yet private missions like SpaceX's planned Starship flights aren't bound by the same strict protocols. A single stray bacterium could hitchhike to Mars, potentially skewing the search for native life or, worse, triggering an ecological domino effect we can't predict. Astrobiologists warn that Europa's subsurface ocean, warmed by tidal forces, might be the most likely place for extraterrestrial life in our solar system. If a future probe melts through its icy shell, could we accidentally introduce Earth organisms that outcompete native life, or worse, consume it? The line between exploration and invasion has never been thinner. Ownership complicates the picture further. Asteroid mining promises platinum and rare earth metals, but who gets to profit? Luxembourg and the US have passed laws allowing companies to claim space resources, while the Moon Agreement, a less ratified treaty, calls for equitable sharing. Critics argue this could replay Earth's colonial history, where powerful nations exploit off-world riches while leaving others behind. Imagine a future where lunar helium-3, a potential fusion fuel, is controlled by a handful of corporations, dictating energy access for billions. The ethical frameworks we build now will shape whether space becomes a commons or a corporate frontier. Even artificial intelligence, our silent partner in exploration, raises moral questions. Autonomous rovers deciding where to drill or AI classifying potential life signs must balance efficiency against caution. An algorithm prioritizing speed might overlook a faint biosignature, while one programmed for excessive caution could stall missions indefinitely. NASA AI ethics boards are drafting guidelines, but the universe doesn't wait for committees. When the Europa Clipper arrives in 2030, its AI will face split-second choices: ignore a strange chemical signal to stay on schedule, or divert precious power to investigate. The heart of the dilemma is this: technology outpaces wisdom. We can land on Mars, but do we know how to tread lightly? We can mine asteroids, but can we share their bounty? The answers won't come from treaties alone. They'll emerge from a global conversation, one that includes scientists, ethicists, and even philosophers. Because space isn't just a new frontier, it's a mirror reflecting back the best and worst of what we bring to it. The stars offer infinite possibilities, but only if we're wise enough to recognize that exploration isn't just about reaching outward, it's about growing up. Buried deep in Earth's crust and etched into the rings of ancient trees lies a hidden archive of cosmic violence, the fingerprints of long-dead stars that exploded in our galactic neighborhood. These aren't just distant astronomical events. They're celestial time stamps that have shaped our planet in ways we're only beginning to understand. Take the seabed off Japan, where layers of sediment contain an unusual spike in iron-60, a radioactive isotope that forms almost exclusively in supernova. Dated to roughly 2.5 million years ago, this interstellar dust coincides with the Pliocene epoch's dramatic climate shifts, a period when Earth cooled rapidly and grasslands expanded, possibly altering the course of human evolution. The real detective work begins when we connect these geological clues to modern astronomical data. By mapping nearby stellar nurseries and backtracking the motion of stars, scientists have identified a likely culprit for that iron-60 deposit, a group of massive stars in the Scorpius-Centaurus association that went supernova as our solar system passed through their debris field. The timing is uncanny. Those explosions would have bathed Earth in intense cosmic radiation for thousands of years, potentially punching holes in the ozone layer and increasing mutation rates in terrestrial life. Some researchers even speculate these events could explain sudden bursts of evolutionary innovation, like the rapid diversification of hominids around that same period. But supernova signatures aren't just locked in rock, they're written in living trees. In 774 CE, Japanese cedar trees recorded a mysterious carbon-14 spike in their growth rings, while Antarctic ice cores from the same year show a surge in beryllium-10. Both isotopes form when high-energy cosmic rays slam into our atmosphere, suggesting a brief but intense radiation storm. The source, either a supernova or an exceptionally powerful solar flare, but the smoking gun appeared when astronomers found a nearby supernova remnant, the sprawling debris of a star that would have been visible in daylight for weeks when it exploded. Modern technology lets us reconstruct these ancient cataclysms with startling precision. Particle accelerators can recreate the nuclear reactions that forged those telltale isotopes, while supercomputers simulate how shock waves from nearby supernova might have compressed the heliosphere, our sun's protective bubble, allowing more cosmic rays to reach Earth. The implications are staggering. A supernova within 50 light-years today could trigger mass extinctions by sterilizing the planet's surface with radiation. Yet, paradoxically, these same apocalypses may have been essential to our existence. The heavy elements in our bones, the iron in our blood, all forged in stellar explosions that seeded the cosmos long before Earth formed. What's emerging is a profound realization. Earth doesn't exist in isolation. Our climate, our biology, even the minerals beneath our feet are products of an ongoing cosmic conversation. One where dying stars whisper their secrets across millennia and modern science learns to listen. Every atom in your body carries echoes of these explosions, making us literal stardust shaped by the very catastrophes we're now learning to decode. The universe doesn't just surround us, it's within us, written into the deepest layers of our world and our DNA. The universe has a funny way of defying our expectations, especially when it comes to life. We once thought Earth's conditions were the gold standard for habitability, but then we found microbes thriving in boiling acid, buried under miles of ice, even swimming in nuclear waste. If life can cling to existence in these extreme pockets of our own planet, why not on the frozen moons of Jupiter or the scorching skies of Venus? The search for life beyond Earth has shifted from hunting for Earth twins to probing the most hostile corners of our solar system, places where the rules of survival seem rewritten by nature itself. Take Europa, Jupiter's icy moon, where a global ocean sloshes beneath a crust of frozen water as hard as granite. The pressure down there is crushing, the temperatures near freezing, and sunlight never reaches it. Yet NASA's upcoming Europa Clipper mission will skim just 25 kilometers above its surface, using ice-penetrating radar to map the hidden sea below. What makes this ocean so compelling isn't just the water. It's the hydrothermal vents likely dotting its floor, spewing mineral-rich plumes into the darkness. On Earth, such vents are oases, hosting entire ecosystems powered not by sunlight but by chemosynthesis. Tube worms, blind shrimp, and heat-loving bacteria thrive in these alien conditions, suggesting Europa's depths could harbor similar surprises. The Clipper won't land, but it will sniff Europa's plumes for amino acids, lipids, or even molecular structures that hint at biological activity, a cosmic breathalyzer for life. Then there's Venus, a planet that went from Earth's twin to hellish wasteland in our imaginations until scientists spotted phosphine in its clouds. This stinky, flammable gas is hard to make without life, at least on Earth. Venus's surface is a furnace hot enough to melt lead, but 50 kilometers up, its clouds are a balmy 30 degrees Celsius, with droplets of water and even traces of organic molecules. MIT researchers have proposed that microbes could float there, encased in acid-resistant shells, riding wind currents like cosmic plankton. NASA's Da Vinci mission will plunge through Venus's atmosphere in the 2030s, its instruments analyzing every layer for chemical imbalances that might betray unseen biology. Even if the phosphine turns out to have a non-living explanation, Venus reminds us that life could exploit niches we've barely considered. Mars, long the poster child for extraterrestrial life searches, still holds secrets in its icy poles and subterranean brine. The Perseverance rover's discovery of organic molecules in Jezero crater, a former lakebed, points to a time when Mars was wet and chemically active. But the real jackpot would be finding extremophiles alive today, perhaps in deep aquifers where liquid water lingers. Future drills like those on ESA's Rosalind Franklin rover could probe meters below the surface, where radiation can't reach and ancient microbes might persist in suspended animation. Beyond our solar system, the possibilities explode. Exoplanets like K218b, a Hycean world with a hydrogen-rich atmosphere and global oceans, or tidally locked planets with permanent day and night sides, could host life in forms we've never imagined. The key is technology, spectrographs sensitive enough to detect metabolic byproducts in alien atmospheres, or probes capable of sampling extraterrestrial oceans without contamination. Finding life in these extreme environments wouldn't just add to our list of inhabited worlds, it would redefine life's boundaries. A second Genesis, independent of Earth's, would suggest the universe is teeming with biology. Even if we only find Earth-like microbes clinging to survival on Europa or Enceladus, it would prove life can spread like cosmic moss, thriving wherever there's even the faintest whisper of energy and liquid. The message is clear: life doesn't play by our rules, it writes its own, and the universe might be far more creative than we ever dreamed. We know the universe is made of stars, planets, and galaxies, but here's the catch: half the ordinary matter we expect to find is simply gone. Not dark matter, not exotic particles, but the same protons and neutrons that make up everything from your coffee mug to distant quasars. Cosmologists call this the missing Baryon problem, and it's one of astronomy's most embarrassing gaps, like meticulously inventorying a warehouse only to realize half the shelves are empty without explanation. So where is it hiding? The leading theory points to the cosmic web, those vast, thread-like filaments of gas stretching between galaxies, too faint and diffuse to see with traditional telescopes. Picture the universe's structure as a sponge. Galaxies cluster where the material is densest, but most of the volume, and likely most of the missing matter, lies in the porous gaps between. These filaments aren't empty, they're searing hot plasma, heated to millions of degrees by ancient shockwaves from galaxy collisions and supernova. At these temperatures, the gas emits X-rays, but so faintly that until recently, they were lost in the cosmic static. That's where instruments like the European Space Agency's Newton and Japan's Hitomi satellite come in. By stacking thousands of observations, astronomers have begun teasing out the X-ray glow of these filaments, like spotting a single lit match in a foggy stadium. The data reveals a clue. The missing matter isn't uniformly spread. It clumps in unexpected ways, concentrated near galaxy clusters where gravitational forces trap it like flies in a spider's web. Some of it might even exist as warm, hot intergalactic medium, or WIM, a frustratingly vague term for gas that's too hot for optical telescopes but too cool for X-rays to easily detect. But X-rays aren't the only tool in the hunt. The Sunyaev-Zeldovich effect, a subtle distortion in the cosmic microwave background caused by hot gas scattering photons, offers another path. Telescopes like the Atacama Cosmology telescope in Chile scan for these distortions, mapping the invisible scaffolding between galaxies. Meanwhile, fast radio bursts, those millisecond cosmic flashes, serve as natural probes. As these bursts travel through space, their signals slow slightly when passing through ionized gas. By measuring how much different frequencies are delayed, astronomers can estimate the density of electrons along the burst's path, effectively weighing the invisible matter it traversed. The stakes are higher than just balancing a cosmic ledger. If the missing matter is tied to the cosmic web, its distribution could reveal how galaxies form and grow, siphoning gas from these filaments like roots tapping underground streams. Its temperature and motion might even encode secrets about dark energy's push on the universe's large-scale structure, and if against all odds, it's not found in these expected places, that would mean our understanding of nuclear physics after the Big Bang is fundamentally flawed, forcing a rewrite of how ordinary matter condensed from the primordial soup. Every discovery peels back another layer. Recent observations suggest some missing matter might exist as ultra-diffuse clouds floating in galactic halos, invisible because they're too cold to emit light but too sparse to block it. Others propose it was blasted into intergalactic space by supernova winds, a cosmic spill we're only now learning to trace. The beauty of this mystery is its humility. Unlike dark matter's grand enigma, the missing Baryon problem doesn't require new physics, just better tools and sharper eyes. It's a reminder that even the ordinary can hide in plain sight, and that the universe always keeps a few receipts tucked away. As telescopes grow more sensitive and techniques more clever, we're not just hunting for matter, we're learning how to see the invisible threads weaving the cosmos together. Mars isn't just a destination, it's becoming a blueprint for survival. Picture a habitat rising from the rusty dust, its walls 3D printed from regolith mixed with recycled spacecraft materials, shielding colonists from cosmic rays while solar arrays stretch toward the thin horizon. This isn't a fantasy. NASA Mars Dune Alpha has already simulated year-long missions in Texas, testing how humans cope with isolation and limited resources. Meanwhile, SpaceX's Starship, designed to carry 100 settlers per flight, could slash the cost of Martian migration from trillions to mere millions. But the real breakthrough isn't just getting there, it's staying alive. Closed-loop life support systems like those on the ISS now recycle 98% of water, and experimental bioreactors use genetically modified algae to turn carbon dioxide into oxygen and even edible protein. The challenge: scaling these systems for thousands of people while preventing catastrophic failures, because on Mars, a ruptured greenhouse or failed air filter isn't just an emergency. It's extinction. Lunar cities might happen even sooner. The Moon's low gravity and proximity make it an ideal testing ground for technologies we'll need farther out. The European Space Agency's Moon Village concept envisions habitats built by autonomous robots using lunar soil as concrete, with inflatable modules shielded by meters-thick regolith to block radiation. Recent discoveries of ice in permanently shadowed craters mean colonists could mine water for drinking, farming, and even splitting into hydrogen fuel. Japan's ISpace and NASA Artemis program aim to establish permanent outposts this decade, but the Moon's real value lies in its shipyards. With 1/6 Earth's gravity, launching massive interstellar craft from the lunar surface would take a fraction of the energy required on Earth, turning the Moon into the ultimate cosmic port. Yet the most radical vision lies beyond planets altogether. O'Neill cylinders spinning space megastructures that mimic gravity through centrifugal force could house millions in Earth-like conditions without relying on any planetary surface. Think of them as artificial islands in space, cylinders 16 miles long with lakes, forests, and even weather systems powered by sunlight reflected through massive mirrors. Blue Origin's Orbital Reef Station is a stepping stone toward this future, testing the construction techniques and closed ecosystems we'd need to build these celestial arcs. The materials likely mined from asteroids, where a single metallic rock like Psyche contains enough iron and nickel to supply global demand for millions of years. What ties these visions together isn't just technology, it's adaptability. Martian greenhouses must withstand dust storms that last months. Lunar bases need to operate in 2-week nights where temperatures plunge to -170 degrees Celsius. And O'Neill cylinders require flawless engineering. A single structural failure could doom thousands in seconds. The solutions emerging from self-healing materials inspired by human skin to radiation-deflecting magnetic shields modeled after Earth's magnetosphere are pushing engineering to biological levels of sophistication. The ultimate question isn't whether we'll colonize space, but what kind of civilization will become out there. Will Mars develop its own culture, its laws shaped by scarce resources? Could lunar mining trigger conflicts over who owns the Moon's poles? And if we build O'Neill cylinders, will they become egalitarian utopias or corporate city-states adrift in the void? The technology decides more than survival, it shapes our identity. Every rover deployed, every 3D printed habitat, every algae bioreactor isn't just a tool. It's a seed planted in the sterile soil of the cosmos, waiting to grow into something unimaginable. The future of humanity isn't written in the stars. It's being coded in labs, tested in deserts, and prototyped in orbit, one audacious blueprint at a time. Astronomers are drowning in data, and that's a good problem to have. Every night, telescopes around the world capture terabytes of information, from the flicker of distant stars to the faint whispers of radio waves crossing billions of light years. But here's the catch. Hidden in that avalanche of ones and zeros could be the next groundbreaking discovery, a new type of galaxy, a rogue planet, or even signs of extraterrestrial intelligence. The trouble, no human team, no matter how brilliant, could sift through it all in a lifetime. That's where artificial intelligence steps in, not as a replacement for human curiosity, but as a tireless partner with a knack for spotting the cosmic needles in the haystack. Take galaxy classification, a task that once required astronomers to squint at photographic plates for hours. Today, neural networks like those used in the Galaxy Zoo project analyze millions of galaxy images in days, sorting spirals from ellipticals and flagging oddities like colliding systems or rare ring galaxies. But AI's real superpower is finding patterns we didn't even think to look for. In 2018, a machine learning algorithm scanning Kepler Space Telescope data discovered Kepler 90I, an eighth planet in a distant solar system, one that human researchers had overlooked for years. The AI spotted the faint, rhythmic dimming of the star, a signature buried in noise no human eye could pass. It wasn't just a new world, it was proof that AI could see the universe differently. Then there are supernovae, the universe's most violent fireworks. Predicting these explosions used to be pure guesswork, but now, AI trained on decades of stellar behavior can flag stars on the brink of collapse. Those Wiki transient facilities algorithms scan the sky nightly, comparing new images to old ones in real time. When they spot a sudden brightening, they calculate the odds it's a supernova and alert astronomers within minutes, sometimes before the star's light peak reaches Earth. This isn't just about speed. It's about catching the earliest moments of these cataclysms, when the physics of stellar death unfolds in ways we've never witnessed. The most exciting frontier, anomaly detection. AI excels at identifying the cosmic WTH moments, data points that defy all known patterns. At the SETI Institute, machine learning sifts through radio telescope signals, filtering out earthly interference to spotlight unexplained pulses that might, just might, be artificial. In 2020, an AI scanning old data from Australia's Parkes telescope flagged a bizarre repeating signal that didn't match any known astrophysical source. It turned out to be interference from a microwave oven in the observatory's kitchen, but the fact that AI spotted it at all shows its potential to uncover the truly unexpected. What makes this collaboration so powerful is the division of labor. AI handles the brute force work, crunching numbers, testing millions of hypotheses, and flagging the statistically weird. Humans bring the intuition, asking the creative questions that turn raw data into meaning. Together, they're rewriting the playbook of discovery. The next Einstein might not be a lone genius with a telescope, but a team of scientists and their algorithms, decoding the universe's secrets one anomaly at a time. The cosmos is talking. Thanks to AI, we're finally learning to listen at scale. When Copernicus first suggested Earth wasn't the center of the universe, it wasn't just a scientific revolution, it was a cultural earthquake. Overnight, humanity's place in the cosmos shifted from the starring role to a supporting character, sparking existential crises and artistic movements that still echo today. Fast forward to the Hubble Deep Field image in 1996, where thousands of galaxies filled a patch of sky no bigger than a grain of sand held at arm's length. That single photograph didn't just expand our cosmic horizons. It seeped into films, music, and literature, fueling stories about humanity's smallness and resilience in an indifferent universe. Now the James Webb Space Telescope is writing the next chapter. Its infrared portraits of newborn stars and swirling galaxies aren't just data points, they're cultural touchstones. Digital artists remix Webb's images into viral installations, While philosophers debate what it means to see light from the universe's first galaxies, photons that have traveled 13 billion years to reach us. Religious scholars grapple with scriptures written when the cosmos was thought to be a celestial dome, now confronted with a reality where the heavens stretch beyond comprehension. Even language evolves. Terms like exoplanet and dark energy slip into everyday conversation, reshaping how we describe our place in the grand scheme. This cultural ripple effect isn't new. The discovery of Jupiter's moons by Galileo shattered the medieval belief in perfect heavenly spheres, inspiring poets like John Donne to lament a universe all in pieces, all coherence gone. Einstein's relativity didn't just redefine physics, it influenced Picasso's cubism, where multiple perspectives coexist on a single canvas, mirroring spacetime's fluidity. When Voyager's pale blue dot photo showed Earth as a lonely speck in the void, it birthed environmental movements by framing our planet as fragile and finite. But here's what's different today: the speed at which cosmic revelations spread. A Webb image goes viral in minutes, dissected on social media by millions who have never opened an astronomy textbook. Podcasts and YouTube channels translate black hole mergers into sonic experiences, making astrophysics visceral. Meanwhile, indigenous astronomers bridge ancient star lore with modern science, like the Maori interpreting JWST data through traditional narratives of celestial creation. The universe isn't just being studied, it's being felt in memes, tattoos, and TikTok trends. Perhaps the most profound shift is how cosmic discoveries recalibrate our sense of time. The realization that stars die and galaxies collide on scales beyond human reckoning has birthed long-termism, a philosophy urging us to plan not for decades but for millennia. Artists like Olafur Eliasson create installations mimicking neutron star collisions, inviting viewers to stand for a moment at the crossroads of deep time and human ephemerality. Even our myths are evolving. Sci-fi stories no longer default to alien invasions, but to first contact scenarios steeped in the awe and humility modern astronomy inspires. The irony is beautiful. The farther our telescopes peer into the void, the more they reflect us back to ourselves, not as the center of everything, but as conscious stardust trying to make sense of the miracle that we exist at all. Every cosmic revelation strips away another layer of anthropocentrism, yet leaves us more connected, more curious, and more creatively alive than ever. The universe isn't just out there, it's in our songs, our prayers, and the way we tuck our children in at night, pointing to the stars with stories rewritten by each new discovery. The universe has always been one step ahead of us, crafting puzzles just beyond the reach of our current tools, dangling mysteries at the edge of comprehension. But the next generation of cosmic explorers won't just push boundaries, they'll dissolve them entirely. Picture a telescope that doesn't rely on light at all, but on the spooky connections of quantum entanglement. Imagine photons captured on opposite sides of the galaxy, their properties mysteriously linked, allowing us to piece together images of black holes with resolutions 1,000 times sharper than today's best instruments. Quantum telescopes could peer past the glare of stars to spot Earth-like worlds directly, or map the magnetic fields of distant pulsars in exquisite detail, all by harnessing the universe's own weirdest rules against it. Then there's the quiet revolution brewing in miniaturization. Think of nanobot probes no larger than a grain of sand, riding laser beams to nearby stars like breakthrough Starshot's vision. But instead of a single flyby, these tiny explorers could swarm a target, dispersing across an exoplanet's atmosphere or ocean to analyze chemistry, temperature, and even seismic activity. Powered by ambient starlight or microscopic nuclear batteries, they'd transmit data back via quantum-encrypted signals, creating a real-time network of interstellar sensors. And if they find something extraordinary, they could self-assemble into larger structures, constructing communication arrays or sample return pods from local materials. It's not just exploration, it's evolution, with humanity's curiosity encoded in machines smaller than a cell. But the most profound leap might come from the machines themselves. Sentient AI probes, endowed with not just programming but genuine curiosity, could make decisions no Earth-bound scientist could anticipate. Picture an autonomous spacecraft at Saturn's moon Enceladus, analyzing plume chemistry in real time, then choosing, on its own, to dive deeper into a promising vent. Or an AI at the helm of a deep space observatory, redesigning its own search algorithms after spotting anomalies in exoplanet atmospheres, iterating faster than any human team. These wouldn't be tools, they'd be partners, capable of creative problem-solving in environments where light-speed delays make remote control impossible. The Voyager probes carried golden records to speak for us. The next messengers might speak for themselves. Of course, the wildest possibilities are the ones we haven't imagined yet. Dark matter detectors might evolve into dark matter harvesters, tapping into the invisible scaffold of the cosmos for propulsion. Biological probes could use synthetic DNA to store data or even grow instruments on site, blending technology with nature. And what if we discover entirely new cosmic phenomena, dimensions beyond our perception, or physics that renders our current tools obsolete? The history of astronomy is littered with moments where new instruments revealed truths we didn't know to question. The future will be no different. One thing binds all these visions: humility. Every time we've built a better telescope, launched a more capable probe, or written a smarter algorithm, the universe has responded by showing us how much we've missed. The galaxies we thought were rare turned out to number in the trillions. The empty space between them brims with invisible matter. Even time itself behaves differently near a black hole. So while we dream of quantum lenses and thinking machines, the cosmos is already dreaming bigger. The next frontier isn't just about the tools we'll build. It's about preparing to be astonished by what they reveal and having the courage to let them lead us into the unknown. From AI to quantum sensors, technology has become our guiding torch in the cosmic dark, not just illuminating what we know, but revealing how much we've yet to discover. Think about it. Every time we build a tool sensitive enough to listen for gravitational waves or an algorithm clever enough to spot planets in noise, we're not just answering old questions. We're stumbling upon mysteries we didn't even know to ask. Take the James Webb Space Telescope. Designed to study the earliest galaxies, it unexpectedly found fully formed cosmic giants where theory predicted only infants. The universe, it seems, loves to surprise us, and our tools are the keys to its best-kept secrets. But here's what's truly exhilarating. The frontier isn't just light years away. It's in the labs where scientists craft quantum sensors so precise they can detect a black hole's hum, or in the code of neural networks that sift through starlight for patterns no human eye could see. Consider LIGO gravitational wave detectors, machines so sensitive they measure disturbances smaller than an atom's nucleus. When they caught the ripple of two neutron stars colliding, it wasn't just a triumph of engineering. It was a new language, a way to hear the universe's most violent symphonies for the first time. And that's the magic of this moment. We're not just observers anymore. We're participants, reshaping our understanding with every dataset, every simulation, every flicker of light from the edge of spacetime. What's next? The horizon shimmers with possibility. Quantum telescopes could peer past the limits of light, capturing images of exoplanets with continents and clouds. AI might decode the chemical whispers of distant atmospheres, flagging gases that scream life against all odds. And dark matter, those elusive particles, could be within reach of next-gen detectors, waiting to reveal the invisible scaffold holding galaxies together. But here's the thing, the greatest discoveries often come from the tools we haven't invented yet. Imagine a probe that harnesses space-time itself for propulsion, or a computer that simulates alternate universes to test the boundaries of physics. The line between science and science fiction blurs faster than ever, and that's where the adventure lies. So yes, the journey has just begun, but it's not just a journey outward, it's inward too. Every time we unlock a cosmic secret, we're also uncovering something about ourselves, our ingenuity, our resilience, our insatiable need to understand the stars. The universe isn't just a place we explore, it's a mirror reflecting back our potential. And if history's taught us anything, it's that the next revelation is always more astonishing than the last. So keep looking up, and who knows, the next great discovery might have your name on it. Don't miss a moment of the adventure. Subscribe now, and let's uncover the cosmos